So far in this unit, you have been introduced to the mole, and I've also introduced you to the process of unit analysis. And now what we want to do is take the unit analysis method, or that line of thinking, and apply it to calculations involving the mole. And it's really important to work towards mastering these calculations involving the mole early on in the course, because you're going to see them over and over again throughout the course. And so by the end of this tutorial, I hope that our goal is that you have some familiarity with a problem-solving approach involving moles, Avogadro's constant, and number of things. And on that note, I want to introduce you to the symbols for those different values. And so the N here, the capital N, represents number of things, and that can be atoms, formula units, molecules, ions, you name it. It's the number of things. The lowercase n right here is the number of moles. That's the standard symbol for number of moles, and of course it has the units of moles. And then Avogadro's constant, that's the number of things in a mole, as we talked about in the mole tutorial, and the units for it are things per mole. So I've talked about trying to take a unit analysis or a units-based approach to our calculations, and so if we look at that, if we're trying to find the number of things, so the big N, we would multiply moles times things per mole, or we'd multiply the number of moles times Avogadro's constant. And if we were finding the number of moles, we would either divide the things by things per mole, or as I would prefer to see you write it, you'd multiply things by the moles per thing, so that the units cancel out, the things cancel out, and you are left with moles. However, some of you may be more comfortable with a formula approach. And so the relevant formula here for finding the number of things is big N equals little n times NA, or little n equals big N divided by NA. And we can summarize that relationship in a triangle. And the triangle that relates those three variables is shown right here. And so to find big N, you could multiply small n by NA. To find little n, you would divide big N by NA, or not that you are going to find Avogadro's constant very often, but to find it, you would divide big N by little n. And now that being said, I talked about really trying to focus on a units-based approach, because I think it offers a more flexible approach to problem solving, but I am not going to demand that you do that. So you take the approach that is more comfortable with you, either a formula approach or a units-based approach, but the problems that I will show you, the examples that I will show, will largely be using a units-based approach. So let's take a look at the example. So we are given 4.25 moles of glucose, which is C6H12O6, and we are asked to determine the number of glucose molecules. Well, I'm going to take a grasp problem-solving approach here. And again, you don't have to follow this exact method. You don't necessarily have to write down the G, the R, the A, the S every time. But it's a good idea, and I certainly, from a communication perspective, I do want to see this information shown in the problem. So I have one piece of information explicitly given in the problem, and that is the number of moles of glucose. But also implicitly, because I know that I need to find the number of molecules, a conversion factor that I'm going to use, or a piece of information that is useful, is the Avogadro's constant, which is 6.02 times 10 to the 23 molecules. And I know that's going to be useful because what I'm asked to find is number of molecules. And so when I set that up, I'm going to write down the symbol for what I'm trying to find, the number of glucose molecules. And I am then going to write down the piece of given information, the 4.25 moles, and then I'm going to take that conversion factor and arrange it in such a way so that the units, the moles, will cancel out, and I will be left with units of molecules, which is my desired unit right here. And so now it's just a matter of multiplying the values that I've been given, and I get my 2.56 times 10 to the 24 molecules. I have a quick statement to summarize that. And then I do a check. Now, for simple problems like this, a check isn't always necessary. But you might want to even do this in your head as you're kind of going along to see if the answer is reasonable. And so we have my check was, I think that this is a reasonable answer because the number of glucose molecules that we calculated here, the 2.56 times 10 to the 24, is greater than that of Avogadro's constant. And that makes sense because in Avogadro's constant, that Avogadro's constant is equal to 6.02 times 10 to the 23 things per mole. So in this case, molecules per mole. So my answer should be greater than Avogadro's constant because I have more than 1 mole. I have 4.25 moles. Taking a look at part B of question 1, we were asked to find the number of oxygen atoms that exist in this sample of glucose molecules. And so recall that we were given 4.25 moles of glucose. From the chemical formula for glucose, we know that there are 6 oxygen atoms, as seen right here, per molecule of glucose. And we also know that we have Avogadro's constant, 6.02 times 10 to the 23 molecules per mole. And so we have these two conversion factors to help us arrive at our final answer with the unit of atoms. And in order to do that, we are going to, in our analysis, we're going to find the number of oxygen atoms total. And just one little note here that, so I have the symbol, the capital N for number of atoms or number of molecules, or whatever the case may be. But I want to include in the subscript here just a little bit more information about what the symbol is representing. And so in this case, I've got the number of oxygen atoms total. If we look up top at the number of moles, so it's the number of moles of glucose. And so just kind of a useful communication tip for you to use going forward. And so I'm going to write down my given piece of information, which was the 4.25 moles. And now I have those units of moles, and I know that I want to get rid of them because my units for my final answer should be in atoms. And so I take a look at a conversion factor that has moles in it, and that of course is Avogadro's constant. And so I'm going to include this conversion factor in such a way that the moles are arranged numerator and denominator, and they can be cancelled out. And so I am now left with units of molecules, but I know that I want to get rid of molecules, and I need to incorporate atoms. And that's where my second conversion factor that connects atoms and molecules comes in. And so in incorporating that, we have the 6 atoms per molecule, and that's arranged in such a way that I've got molecule in numerator, molecule in denominator, they cancel out. Now the only units that I'm left with are atoms, and I multiply the 3 numbers, and I have my units, and I arrive at this number. And as a quick check to see if my answer makes sense, referring back to part A, I know that my answer should be larger than the answer in part A, since I'm talking about not just molecules, but the number of oxygen atoms in the sample, and since there are 6 oxygen atoms per molecule, there should be more oxygen atoms than molecules. Similar approach here in question number 2, with one twist, I guess, and that is that this time we are looking for the number of moles, and we are given the number of atoms. And so I indicate the given information here, and again we've got Avogadro's constant to help us. Note that this time now the units for Avogadro's constant are atoms per mole, because the units for Avogadro's constant are flexible depending on what type of substance it is you're working with. And of course what we're looking for is the number of moles of iron, and the units for that are moles. And so we write the number of moles of iron here, and then write down our given information, which was the 3.0 times 10 to the 25 atoms, and use the conversion factor. Now note that the conversion factor is arranged in such a way that I have atoms in the numerator, atoms in denominator, and they are able to cancel out. A common mistake though is to write the 6.02 times 10 to the 23 in the numerator. Remember that the unit reads, we have 6.02 times 10 to the 23 atoms, and so the number and the units have to stay together, and we have that many atoms in 1 mole. And so keeping that in mind, you will place your numbers in the appropriate spot, as well as place your units in the appropriate spot. And so we see that the only units that we're left with are moles, and once we divide this by this, we get there are 50 moles. And that answer makes sense because we know that, or hopefully we have a sense from looking at the given piece of information, it's bigger than Avogadro's constant. And since Avogadro's constant are the number of things, in this case the number of atoms in 1 mole, we would expect that this number represents more than 1 mole. And in fact, it does. So hopefully now, after seeing some examples of unit analysis being applied to mole calculations, you're willing to give it a chance. You are willing to try a few problems and see if it's something that works for you. Certainly, as I said before, it's something that I recommend that you do. It gives you much more flexibility with your problem solving. But even if you go back to a formula-based approach, still really important to pay close attention to your units and include your units throughout your calculations.